So let's move on to heat engines. So how do we turn heat into work? All right, work. The main problem in power generation is getting the heat. Once you get the heat, you can turn this into work, okay? And we'll talk about this in a minute. So work can be sort of sorted into useful work, meaning mechanical work, okay? So like turning something or moving something up and down, or electricity, meaning the stuff that you get out of the wall, okay? The way we get this work is either mechanical energy, so wind, water. So what could you think of that would use mechanical energy to convert stuff into electricity? Well, there's like dams and wind turbines, all right? You can also use heat, and the way that you get heat is either through chemical energy, so you can heat stuff up using coal, gasoline, natural gas, hydrogen, or nuclear energy, and nuclear energy just uses nuclear reactions to generate heat. But all of these things create a heat differential. So you create something really hot, and you either create steam that turns a turbine, or you create some sort of flow, okay? These sort of are our global energy problems. So how do we generate heat using these different things? We find that, natural gas and gasoline and coal and nuclear energy, these all have awful waste products that we have to deal with. The key is going from heat to work, okay? So once you get the heat, you can turn it into work. Now, of course, if you use solar energy, you kind of skip all of this, right? Because you can go straight to the electricity form. Although there are several different kinds of solar energy. There's photovoltaic cells where you can actually start creating a current by getting photons hitting a solar panel. But you can also use solar energy, meaning you can focus parabolic mirrors on a particular bit of water and heat it up, and then you're back to heat, right? So you're back over here. Remember, all motorized vehicles other than purely electric vehicles use heat engines for propulsion. Now, where does that come from? Well, that's the combustion of gasoline, and that might charge batteries. Hybrid vehicles use internal combustion engines to help charge the batteries for an electric motor, or they use some sort of gas electric motor hybrid, okay? So remember, work is defined as the integral of under the PV diagram curve, okay? So for instance, work done by a heat engine, if you have your force coming from your gas and your force coming from outside as your environment, right? The environment can compress the gas, and that way your environment is in the same direction as your displacement. This is a compression. But remember, work system is equal to the negative work of the environment. So this is your work system, okay? And we want to change the first law of thermodynamics to deal with engines. So remember, this is the heat added by the system, this is the work done by the system, and this is the change in thermal energy. When we're talking about heat engines, we really want to talk about the work done by the system, because a heat engine is something that actually generates energy and generates either electricity or motion, all right? So when you have some sort of engine, you want to know the work the engine does, therefore the work done by the system. You don't care about the work done outside of the engine because you can't use that, okay? So this is the way we define the first law of thermodynamics for heat engines, okay? Remember, heat transferred into a system is either used to do work or stored within the system as increased thermal energy. And what we care about is the work that these systems do. So let's talk again about energy reservoirs, okay? What happens if you throw this ice cube into the ocean? We talked about this a little bit earlier in chapter 19, but we discussed this using terms we used in class. So heat from the ocean water goes into the ice, okay? So that's a positive Q. It melts the ice, which changes the ice, okay? So it changes the way the ice is structured. It's a phase change, and then it also is kind of a volume change. Now, does this change the temperature of the ice? Well, yeah, it goes from freezing to whatever the ocean temperature is. But does it change the temperature of the ocean? Absolutely not, okay? So an energy reservoir is something where you can add or subtract heat from it. Q can go in or out, and it doesn't change the reservoir itself, okay? So an energy reservoir is something so large that the temperature does not change when heat is transferred. So remember, if heat's transferred into a hot reservoir, from the hot reservoir to the system, so we're going to talk about hot and cold reservoirs. If heat's transferred from a hot reservoir to the system, you call that Q sub H. If heat is transferred from a system to a cold reservoir, we call that Q sub C. Okay, so remember, these are always positive. One goes in, one goes out. So this is a different way of treating heat than we've been treating it previously, where heat was either plus or minus depending on whether it was coming or going from the system. Now, instead of calling it plus or minus, we're going to call it QH and QC. Basically, QH is what we used to call plus Q, and QC is what we used to call minus Q. TH and TC are the temperatures of the hot and cold reservoir, and that's going to give you some change in thermal energy. All right. So remember, you can go like this. You can transfer heat into your system, you can transfer heat out of the system, and then Q, just regular Q, is going to be the net heat transferred into the system. Okay, so you have some going in, you have some going out. You subtract QH and QC, and that gives you Q. Okay, so for instance, if heat is transferred into the system from a fire, heat can be transferred out of the system through ice. Okay, hot reservoir is always drawn at the top. The cold reservoir is always drawn at the bottom. All right, and if the temperature doesn't change, what's the relationship between QH and QC? Well, we're not really changing thermal energy. We're not really changing work. So thermal energy is 0. Work is 0. That means Q is 0, which means QH has to be equal to QC unless you have some actual useful work going in and out of the system. All right. So that's where we're at. So if we want to turn work into heat, all right, well, you can do something like this where you take rocks out of the ocean, rub them together. That's work, right? You change the temperature, that's thermal energy, and you throw the rocks back into the ocean. That means your total change in temperature is 0, all right? So we have work, we've converted into heat, but this doesn't do any actual useful stuff, okay? Remember, Q and work are the same. That means work in is equal to QC. This is 100% efficient, but you can't actually use any of that heat or work to do anything, okay? So who cares? All right, let's move on and talk about how we turn heat into work. So let's talk about an isothermal expansion. Looking at the first law, for an isothermal expansion, what do we know about our change in thermal energy? It's isothermal, so that means our change in temperature is 0, which means our change in thermal energy is also 0, okay? Which means Q is going to be equal to the work done by the system, which means in this case, QH is going to be equal to work done in the system. And any useful device that transfers heat into work has to return to its initial state at the end of the process. Remember, we want cyclical things, and the initial state means it has the same state variables. So P, V, T, change in thermal energy, okay? So remember, heat goes in, gas expands isothermally, and all the heat is converted into work. But in this case, the gas is going to be in a different state, okay? If you have an isothermal expansion, the temperature stays the same and thermal energy stays the same, but work and heat both change. So heat engines are going to be closed cycle devices that have to return to their initial state, right? Your engine isn't very useful if it can't repeat what it does multiple times. So that means you have to start and end at the same PVT and thermal energy. All right. So remember, a heat engine is a closed cycle device that extracts heat from a hot reservoir, uses some of it to do useful work, and some of it gets returned to the closed reservoir. Okay. Remember, Q is equal to QH minus QC. All right. So a closed cycle device means, of course, you start and end at the same state. So on a PV diagram, it would start and end at the same point. That means your change in thermal energy is 0 at the end of a full cycle. So that means your work out is equal to Q, right? This is the work done per cycle by a heat engine. So every time you have a cycle, you get a certain amount of energy out of your engine. And that's going to be equal to Q, which is equal to QH minus QC, okay? So here you have your hot reservoir up here. You use that to transfer heat into your system, which is right here. That heat goes to both work, the output of work, and to your cold reservoir, okay? This is a little bit of waste. This is what's used as useful work. So efficiency, right, is how much of the heat that you put in is converted to work, because obviously some of the heat's coming out and you're not using it in W. So your efficiency is defined as the total work divided by the heat you started with. All right, so efficiency is work out divided by QH. And of course, because we know work is equal to QH minus QC, you can convert it to this. So just convert this to QH minus QC. That gives you QH over QH minus QC over QH. So this is just another way to write the same thing. Okay? All right. Now we're going to rank in order from smallest to largest the work out performed by these 4 heat engines. Okay? So I'm going to have you pause this, think about it, come up with an answer, and then push play again when you know what your answer is. Okay, we're back. Turns out the answer is D. Now, how do you get this? Well, you just subtract QH minus QC, because remember, work out is equal to Q, okay? So here, 100 minus 60, that's 40. 200 minus 160, that's also 40. So these two are the same. A and B are the same. 90 minus 60, that's 30. So that means C is going to be smaller than 40. That's going to be smaller than A and B. And 90 minus 40, that's 50. So D is going to have the largest amount of work at 50. These are both going to have 40, and this is going to have 30. So the largest amount of work is D, followed by A and B together, and then C should be the smallest. Okay? So let's talk about heat engines. We need something cyclical. So here's an example of a heat engine. We'll start with our initial state, okay? We have a gas in a cylinder with a movable piston. The movable piston has a mass m on top of it, okay? Then we turn up the heat. Heat goes in to our system, right? It goes into the gas, and the gas expands, all right? Now, what's being kept the same here? We have the same mass on our piston in both cases, and we're adding heat. So this is considered an isobaric expansion, because remember, pressure only depends on the cross-sectional area of the piston and the mass of the piston, and these things have not changed from this state to this state. So this is an isobaric expansion. Then you lock this piston in place and remove the mass and let heat go out. Well, if you lock the piston in place, that means the volume can't change, which means this is isochoric cooling, okay? Heat's coming out, so you have isochoric cooling from here to here, all right? Then, if you slowly increase the external force, if you push down slowly, you cause a compression, that's going to be an isothermal compression, and slowly is the key word here, okay? So we have isobaric expansion, isochoric cooling, and then an isothermal compression. So let's draw the PV diagram of what's going on here, okay? The PV diagram should look something like this. So here we start in this initial state. So that's this, okay? Then we use this isobaric expansion. So you can see the pressure remains the same. There's heat going into the system coming from the fire, so that's heat in. And then we get to state 2. Here you remove the mass, okay, lock the piston, then you get isochoric cooling. So heat's going out of the system as you go from 2 to 3, and you can see it's isochoric because it's vertical. Then last but not least, okay, you slowly increase the force, meaning you have an isothermal compression, all right, and heat leaves your system while you do this slowly. So this is your PV diagram for this heat engine. And since you get back to the same state at the end, you can start this all over, okay? So let's try out an example. So we're going to analyze the heat engine to determine the net work done per cycle, and then we're going to see the engine's thermal efficiency and the engine's power output if it runs at 600 rotations per minute. So if it goes through 600 cycles every minute. All right, and there's some constants given here.
So to start out with, we're analyzing this heat engine, and we're trying to figure out the work done per cycle. And in order to get the work done per cycle, what we really need to do is integrate in the area enclosed, okay? So in order to integrate the area enclosed, we really have to add up all of the work done by each phase. So from point 1 to point 2, from point 2 to point 3, although that one, since it's isochoric, isn't going to be that big of a deal. And then also from point 3 back to point 1 along the isotherm. The first one's easy. It's just a rectangle because, remember, it's P delta V. So this is the area that we're integrating over to start out with. This is the work done by the process going from 1 to 2. So in order to do that, we're just calculating the area of a rectangle, which is base times height, or P times the change in volume. So pressure times the change in volume. We have to do this in pascals and meters cubed. So 200 times 10 to the 5th pascals, 400 times 10 to the negative 6 meters cubed. That's going to give us about 80 joules. Then from 2 to 3, remember this is an isochoric process, meaning there's no volume change, meaning there's no work done in this part of the process. So then finally, to go from 3 back to 1, this isothermal process, we have to integrate along this isotherm. And so that's a little bit more complicated. Basically, you're integrating an inverse curve that gives us a natural log. And remember, since it's an isotherm, pressure and volume are not constant, but P1 times V1 should equal P2 times V2. Remember, that whole term is constant. It should also be equal to nRT because of the way that PV equal nRT works. So we plug this in. We see that the volumes halved, so we don't have to put in the actual volumes, we just put in the ratio. And this gives us negative 44 joules. And it's negative because remember, we're integrating sort of backwards along the volume axis. But also because we know we want this area inside of this sort of triangle thing. So when we add up all of our works, we basically get 80 joules minus 44 joules, and that's going to give us a 36 joules of work done by the whole cycle. Okay. On to part B, we're going to figure out the engine's thermal efficiency, and the thermal efficiency requires both work and heat. We have an equation that's something like E equals, work output, right, by the system, so work done by the system over QH, which is the heat that goes into the system, not the heat coming out of the system. We already know work because we calculated that in part A. So that's going to be 36 joules still. That's the work done by this engine, right? So that's the area inside of the cycle. Now we need to calculate the heat. And in order to do that, we can sort of guess, knowing what we know, what QH is versus, what the heat going in is versus the heat going out. But just to go through the whole calculation, we'll do all of the math. And when we get a negative sign, that'll mean heat is leaving the system. When we get a positive sign, that means heat's going into the system. And so we're going to calculate all three processes. So we have a constant pressure process, a constant volume process, and a constant temperature process. They all have slightly different ways of calculating heat. So for our constant pressure, 1 to 2, that process, it's NCP, the C for constant pressure, delta T. But then we run into another problem where we actually don't know what the number of moles is, because for cycles we don't always need to know that. And so that takes us back to PV equals nRT. We do know the pressure, the volume, the temperature, and the constant at any one point. So we plug this in, do our calculation, and get our number of moles so we can start calculating heat. Okay, and this is just a review of something we already know how to do. So we're taking just taking any point on the graph works. So in this case, we've taken point 1, and we know the pressure, volume, and temperature at that point. Because remember, at every point on this graph, if you take PV divided by RT, it should give you the same number of moles. Okay, oops. All right, so going back to this, we have 0.016 moles, so pretty small amount of gas there. And then we can plug that into our heat equation for process 1 to 2, which is our isobaric process. Okay, so we have 0.016 moles. We're going to multiply that by 20.8 joules per mole Kelvin, which is our CP, right, for a monatomic gas. So that's basically the heat capacity for a monatomic gas. And then we also need to know the change in temperature. And because we know the volume and the temperature and its constant pressure, we can use our process we know from just doing PV diagrams to figure out our new temperature. So we do this calculation. This also comes from PV equals to nRT. Remember, we hold P and N, and of course R is already a constant fixed. So that's going to give us our new temperature. So our change in temperature is 900 kelvins minus 300 kelvins. This gives us 200 joules. You'll notice this is positive, and that becomes pretty obvious because of the way we're subtracting temperature. The final temperature is bigger than the initial temperature. That means heat is going into the system. All right. Next, we're going to calculate our isochoric process. So that's from 0.2 to 3. And because it's isochoric, you have NCV, right? That's the heat capacity for a constant volume process. So the N's the same. Now we're using 12.5 joules per mole Kelvin for C sub V. And then we're going to have our change in temperature going from our back to our isotherm. So now it's 300 minus 900. So you're going to see this is going to have heat going out of our system. It's got to be negative because of the way that we have this set up. So we're going to go negative 120 joules. That would not be considered part of QH. Okay, QH is all of the heat going into the system. This is heat going out of the system. Last but not least, we have this process, this isotherm. In this case, we go back to the first law of thermodynamics. Remember, change in thermal energy is going to be heat and work together, right? So if change in thermal energy is 0, heat is equal to work, and that means we're getting negative 44 joules. Okay, so since we know what the work is and we calculated that in part A, that's negative 44 joules. So that's also not QH. So that means QH is just our 200 joules. Our QC, right, that's our heat leaving the system, is the sum of our two processes that lose heat, so that's 164 joules. And in order to calculate our efficiency, we're just calculating the work, which remember we calculated in part A as 36 joules, that's the work done by our system, divided by the heat into the system, which is 200 joules. So that gives us 18%, and that's our answer for part B. Now, moving on to part C, now we need to figure out the engine's power output if it's running at 600 rotations per minute. So how do we find this? Well, we want to know power. We already know energy, right? So power is just going to be the derivative of energy with respect to time. But in this case, we know time is going to be the time for one cycle, okay? And we know the energy because we have something in joules. So we're going to say, oh, for every cycle, okay, for every cycle we get 36 joules. And that means we have to go back to the rotations per minute. So rotations per minute is the same as cycles per minute. For every cycle, we get this amount of energy. So that's going to be 36 joules of work done per cycle, okay? So now we just have to do a calculation to get power from energy. So we get 36 joules per cycle. This is just a unit conversion now. We have 600 cycles essentially per minute, but of course we want our power in seconds, so we're going to have to do a unit conversion, and we know how many seconds are in a minute, so that's good. We know that for every 1 minute we have 60 seconds. And so we're going to do the math here. And this should give us 360 joules per second. But of course, if we're dealing with power, that's actually in watts. A joule per second is a watt. So 360 watts. So here's our first problem, and this is one of the ones I want you guys to really try on your own before really looking through the solution. We have this 1 mole of gas. It's at STP. We've already done that a lot in the last couple chapters. And we're going to see that it experiences a couple different processes. So an isothermal expansion until its volume doubles, an isobaric compression, returning it to its initial state. And it wants us to draw the PV diagram, determine the heat in, the heat out, the work done by the system, and the efficiency for the heat engine. So the previous example was sort of working off of a graph. In this case, we're going to read the words and make a PV diagram and then function from there. So remember, whenever we have STP for 1 mole of gas, that starts with a volume that we calculated way back in I think chapter 17, where we're calculating 1 mole of gas at STP. That gives us 0.0224 meters cubed. Then we see that this is going to give us an isochoric process where the pressure doubles. So if we're going from 101 times 10 to the third kilopascals, we're getting up to 202. So we don't have to do a ton of math there since we know how to double things and we know what we're starting with. And then we're going to have this isothermal expansion, which is a little bit different till its volume doubles. So we know what the doubled volume is. We just take 0.0224 and double it. And we know that an isotherm is an inverse curve. Obviously, I've drawn it not great, but general idea, not a straight line. And then last but not least, we have an isobaric compression, meaning the pressure remains constant and it returns to its initial state. So we're basically just connecting the dots and making sure they're on a horizontal line. So we know we have our N of 1 mole, so we're not going to have to calculate it this time. And we're going to start, we drew our PV diagram. It looks pretty good. Make sure you've labeled your units and all of that stuff. And then we're going to start to determine our heat and work. So the PV diagram gives us P1, V1, P2, V2, and P3, V3, but we still need to find temperature in order to find the heat. And then we're also going to need to integrate in order to find the work. Okay, so we're going to find temperature for all points in order to calculate our heat for later on. So that means we just use our PV equals nRT holding things constant. We know that we can say that the ratio of P and T for an isochoric process should remain equivalent, and that means we can calculate our temperature to be essentially double the initial temperature from STP, and that's going to be 546 Kelvin, which means if we have an isotherm, we know everything along that purple line should be 546 Kelvin, and now we have all the temperatures we need. So we know the temperature is the same at 2 and 3, and it's slightly different at 1. All right, now that we have that, we can calculate our heats for the most part. So remember, we're calculating heat from NC delta T, and then we're calculating work by integrating the area inside of that curve. So we're calculating these processes, and we can see there's an isobaric and isochoric process, so the heat we know heat specifically, explicitly for isobaric and isochoric processes, and we know for the isothermal process from the last problem, we saw that for an isothermal process, because we use the first law and we know that work should be equal to heat, once we calculate the work under that curve, we can use that. So in this case, we'll go process by process. So going from 1 to 2, the isochoric process, we know the work is 0 because this is a vertical line, and if you integrate under a vertical line, you're going to get 0. And then for the heat, we know that we use NCV delta T because this is an isochoric process, which means the volume is constant, so we use C for constant volume. So that's 1 mole, and since this is a monatomic gas, 12.5 joules per mole Kelvin. Then we take our difference in temperature. That's going to give us a heat of 3.41 kilojoules, which is 3,410 joules. Okay, but it's a lot of energy, so we're going to write it in kilojoules. Then we can do our next process, that's the isothermal process. So for the isothermal process, the work is a little bit more complicated, but remember, work for an isotherm, we know that nRT and PV end up being the same, so we can either use nRT, we can use P2V2, or we can use P3V3. This comes from this integral, because remember, when we're calculating work, we have this PdV, so you can get something that looks like this. This is just showing the derivation. You don't have to do this every time, but if you forget what an isotherm's work looks like, it always works to start from scratch. Remember, nRT is equal to any PV points along that curve, because remember they're equivalent because PV equals nRT, right? So if you have a constant nRT, any P and V that are matched on one point will work. So we know P2 and V2. We could easily have used P2 and V3 as well, but we're going to just use P2, V2. And then we have our natural log of V3 over V2. So because we know those, you can divide these, but really remember it's going to be 2. So natural log of 2. We plug all that in because it's just a ratio. And then we get an answer that looks like, let's see, 3.14 kilojoules, okay? So close to our answer for heat, but not quite. And this is going to be positive because this is an isothermal expansion, meaning the volume is getting bigger. Okay, so that's positive work. Then we have to calculate the heat, but remember, because this is an isothermal process, the change in thermal energy is 0. So that means the work should be equal to the heat. Remember, an isothermal process, anytime you don't change temperatures, change in thermal energy is 0. So that means our heat is also 3.14 kilojoules because we just calculated our work. Okay, so we don't have to do any more math. We just know that those two things are equivalent for an isotherm. And then last but not least, we have our process going from 3 back to 1, right? So that's our isobaric process, and that's going from 3 all the way back to 1. We're going to calculate that. We have a specific Q for that because remember, for isobaric processes, Q is equal to NCP delta T, and since we know our temperatures and we know the number of moles, that should start out pretty straightforward. So the work from 3 to 1, that's easy because it's P delta V, right? An isobaric process is just a rectangle, so we just figure out the area of that rectangle. In this case, the rectangle is going to be negative because we're integrating backwards. That's a compression. That means the volume is getting smaller. So we're going to end up with a negative value. And you could actually write this as 0.0224 minus 0.0448. That would give you the negative automatically. But remember, I sort of fudged it, so we know it's going to be negative. We put the negative sign there. And then we calculate that this is going to give us negative 2.27 kilojoules, okay, which is 2,270 joules. All right, going back to heat, remember this is an isobaric process, so it has its own definition for heat, which is NCP delta T. Now we just plug in the numbers that we already know. This is why we wanted to know temperature at all of these points. For a monatomic gas, the CP is 20.8 joules per mole Kelvin. And then we subtract our temperatures. And this should give us a negative number, meaning heat is going out of the system. And it does, it gives us negative 5.68 kilojoules. So now we have work and heat at all these points. And that means our work out is the total work, right? So we have to calculate, add up all of our works. Obviously for the isochoric it's 0, but then we have 3.14 minus 2.27 kilojoules. That's going to give us a work done by the system, a net work of 0.87 kilojoules. For our heats, there's heat going in and heat coming out. So all of the negative signs indicate heat leaving the system. All of the positive signs indicate heat entering the system. So we'll add up all our positives. That's 3.41 kilojoules plus 3.14 kilojoules. That should give us 6.55 kilojoules. And that's QH. Our QC is all the heat leaving the system. That's going to be our 5.68 kilojoules because we have those negative values. So we can just write that down. And now we have work and both of our heats. You don't necessarily have to call that negative, but you know that it's the negatives indicate that heat is going out of the system. All right, so those are what we asked for. We wanted work out, we wanted QH, we wanted QC. That negative sign is kind of unnecessary, but just for the heck of it. And then if we wanted to calculate the efficiency, remember that's just work out divided by the heat into the system. So, you put a certain amount of heat into the system. This is the amount of work you can get out of it. So you divide 0.87 kilojoules by 6.55 kilojoules. Remember, that's the QH. And this should give us 13.3%. So our efficiency is 13.3.
Ideal gas heat engines. So ideal gas heat engines, that means we're going to use all the stuff that we learned about PV diagrams for ideal gases, and we're going to figure out things like efficiency from our PV diagrams. Okay, so here's a cycle. You can see it's a closed cycle, meaning no matter where you start it, it'll start and end at the same point because it connects all the way around. So remember, work out is the area enclosed by the PV curve. And if you want to do this a little bit more systematically, here's your work done during the expansion. Over here, here's the work done during the compression. When you add your two works up to get your total work, that's your work out. Okay, this is the net work done by your system. All right.
Okay, so once again, I want you guys to try this yourself before you get started. This is basically the same idea, but a little bit less complicated. And you'll notice we have two processes we recognize. We have the isochoric still, and we have the isobaric still. But this is actually not a known process. It's just a random process that's more of a line. But of course, it's nice because it's a straight line. So even though it doesn't follow any of the specific rules, we still can figure out the work by just figuring out the area inside the curve. Okay, so remember, for any cycle at all, we're looking for the area inside the curve to get the work output. Okay, so we're going to start by getting the work. So we're looking for QH, so the heat going into the system, which is not given. We're given all the heat going out of the system, and also the thermal efficiency. Because we know thermal efficiency looks like this, that means we need to find both work out and heat in. So starting with work out, that's the work done by the system in the cycle, so work done per cycle. That's just going to be the area inside the curve. Okay, so if we want to calculate that, that's going to look like this. So that's our work out. And we're in luck because that's just the area of a triangle. And remember, we know the area of a triangle is 1/2 base times height. So we calculate that and it gives us 1/2. The base, we can just look at the, we're going from 200 to 600 here. So that's 400. Unfortunately, this is in centimeters cubed. So there's a conversion that we have to do. Remember, if you have centimeters cubed, that's 10 to the -6 meters cubed, because cubing things creates a lot of stuff. So that's going to be 400 times 10 to the -6 meters cubed, because we need this in meters cubed. And then our height is going to be from here to here, so that's going to be 200. But it's kilopascals, so that's times 10 to the 3rd pascals, just to get the units right, okay? And that's because, remember, a pascal is a Newton per meter, and the newtons go into joules and units, all of that stuff. So when you calculate all of that, you get units of joules. We know it's work. We know it should be units of joules. You can go through and do the crossing out of the different units if you want, but you don't need to in this case. So this is 40 joules after you calculate it. So our work out, that's 40 joules, okay? Now we know what QC is because we could see there's work going out, heat going out of this graph during the isochoric and isobaric processes, so here to here. So our QC, which is not what we're looking for, but what we need to start with, is 100 joules plus 180 joules. It was nice of them to give us that stuff, and that's going to be 280 joules. So remember, QC is just all the heat leaving the system.
if we want to figure out what QH is, we know that the total work output is equal to Q, basically from the first law of thermodynamics, because we know that work minus heat needs to be the change in thermal energy, but since this is a closed system, the total change in thermal energy has to be 0, which also means that the total heat here is going to be 0. So we have QH, or sorry, not 0. The total heat change here is going to be equal to the work out. So that's QH minus QC. Well, now we know work and we know QC. That's the heat leaving the system. So we can calculate QH by just adding those together. So that's going to be our work for our system plus the heat leaving the system. So we put in the numbers we know, that's 40 joules plus 280 joules, which should be equal to 320 joules. So QH, which is the next thing we want to find, is going to be 320 joules. Okay, well, now we can actually find our efficiency because we have everything that we need. So we're going to bring this back over here. So we'll bring this over here. This is going to be equal to 40 joules divided by 320 joules. So work divided by the heat that you put into the system. And then when you add all that together and you do the math, you get 12.5%. And you'll note that for things like efficiency, we're always getting these low numbers, and that's because it's very hard to get an efficient system. And we'll talk about the maximum efficiency we can get, the Carnot efficiency, and even that usually tends to be pretty low, less than 50%. So things are not very efficient, and that's because of the second law of thermodynamics, which means entropy happens. All right. So here's another clicker question. We want to know the thermal efficiency of this heat engine, okay? So I'm going to give you about a minute. Just pause this until you come up with an answer, and then we'll go over the answer, all right? Pause. Okay. Turns out the answer is A. So that's going to be 0.25. Now, how do we get that? Well, remember, thermal efficiency is just work over QH. All right, well, what's QH? QH is given, it's 4,000 joules. What's the work? The work's going to be the area in here. All right, so that's going to be 1/2 base times height, because this is a triangle. So 1/2 0.1 times about 20,000. So 0.1 times 20,000, that's about 1,000. Okay, so work out, that's about 1,000 divided by 4,000, that's about 1/4. 1/4 is 0.25. That's answer A. All right, now notice efficiency doesn't really have units, and so this is why this thing doesn't have units. Okay, so here's a little review on our ideal gas processes that we've learned, everything we've learned so far in the past few chapters. So don't write this down, okay? This is just a summary that you can use when you're doing any of these problems, all right? And to solve heat engine problems, you want to start by drawing a PV diagram, using PV equals nRT and other equations to calculate your state variables, so P and V and T, and then use those to calculate Q, work, and change in thermal energy for each process. You can calculate QH by adding up all the positive Q values and calculate QC by adding up all the negative Q values, and you can end up with all the variables that we're looking for here. Okay? All right.